All right, we are live.
Welcome, lads and ladettes, to Aether Roundtable number 98, Viking Navigation and Sunstones. Take it away, Alan G.
All right. So before we get into the what we're going to watch here, I'll give a little introduction. I was recently told a story of how the Vikings used to use a certain stone that had special properties that would allow them to determine the position of the sun and also determine true north after they had used this, and they could use it when the sun was blocked out by cloudy weather or even when it had set below the horizon, as the globularist would claim, or as we would say, when it's out of our field of vision. And we know that it doesn't, set below the horizon based off of shadow sets. And you can reference Stone's video for how all that works. But the primary important part of this is there's this special crystal that you could hold up at your zenith, and it will it'll change colors, and when it's at a certain color frequency, you'll know that your azimuth is aligned with where the sun's at within 1 degree. So we're going to watch a little documentary of some people reproducing this, and they'll cover the history of it and how this came about. And then we'll get into a paper where this was later quantified, and we're going to go over, how they did that. We're just going to read from that. So it'll be a mixture of movie night and reading night here tonight, where we go over this historical context of how navigation was done by the Viking lads and ladettes. All right, here we go. So we'll watch this video here. This is from the Quest YouTube channel.
1,000 years after their reign, they still have a terrifying
Are you
reputation.
streaming out of Linux?
In popular culture, they're portrayed as axe
Because I can't hear anything.
Yeah.
Oh, 1 second.
I didn't know that you could stream with audio out of Linux, to be honest. I thought you had to be Windows led to do that.
No, it's actually BIS on Linux. Let me know if you can hear it now.
wielding marauders who pillaged their way across Europe. But the Vikings were also maritime masters. They managed to navigate.
Is
We
it
have a
coming
different
through?
definition of BIS.
Is the audio
No.
coming through?
No.
All right, give me 1 second. I think I know what the issue is.
You mean best in slot, right? Not biscuits and shit or whatever.
How dare you? Biscuits. All right, guy. One second. Watch history. Sunstone. Is there audio now? Hang on.
They still have a
Yeah.
terrifying reputation.
Is there audio now?
Affirmative.
Yeah, it's a Discord thing. So they're like, anyway. Not a Linux thing, I promise.
In popular culture, they're portrayed as axe-wielding marauders who pillaged their way across Europe. But the Vikings were also maritime masters. They managed to navigate deadly waters to establish
full
remote
screen that?
colonies across
Oh, there we
Europe,
go. Perfect.
in Greenland, Iceland, and, sorry Columbus, maybe even North America. And they did it all hundreds of years before the use of the magnetic compass. How? What gave the Vikings such an edge? According to ancient sagas, the great Viking king Olaf possessed a sunstone, a magical crystal with unique powers which allowed his people to navigate by the sun, even when it was hidden by clouds or below the horizon. But were these magic crystals real? No one has ever found
What?
one. That
Wait.
is, until now.
Oh, you don't know about your
Below
boy
the horizon? Is that
Magic
what they
Crystal?
said? So they're pointing it beneath their feet, obviously,
No,
because Earth's
no,
a globe. That's how
no,
it works. Oh.
No, so you would think, but no, they just hold it up at their zenny, and they just do a 360-degree rotation. And when a certain alignment happens within the refraction that's going on within that crystal, a certain pattern will be aligned, or it'll like a color will shift within the pattern that's in the crystal, and that will tell you when you're aligned with the sun's azimuth.
That would imply the sun is permanently above the horizon, though.
Oh,
Weird.
oh no, but they can't see it, so it's behind the ball, though.
Right. Crazy.
So
Nice.
so Shane, what's happening is that the ball has like the sun set, because ball, and then the light's being lifted, the light that you can't see is being lifted up,
Okay,
and it's
okay, right,
polar,
right.
and it's like it's polarized. So like when it hits the crystal, there's an effect. There's swamp gas from Venus, like you know what I mean. It's one of those deals.
Recently, a mysterious crystal was discovered on board a shipwreck in England, and it has ignited a fierce debate that has some scientists believing the power of the Sunstone might be real after all. According to the legend, the Viking king Olaf used the Sunstone in dark weather, where it revealed the position of the sun. At the nearby Viking ship museum, it's clear where Norwegians got their nautical skills. This is the Oseberg ship. Built in 820 AD, it is the oldest intact Viking vessel ever found, and it is a thing of pure awesomeness. I mean, just look at this thing. The craftsmanship is nothing short of astounding, and clearly built to last. I'm here to meet with archaeologist Jan Bill to hear about a new theory that may prove that the Sunstone was real. It's really hundreds of years after the Viking Age when the magnetic compass becomes widely used.
Yeah.
Do you think that the legend of the Sunstone is real?
Well, I think that it's much more than a legend. The practical value of that out on sea would be terrific.
Jan tells me that analysis of the crystal found in the Alderney shipwreck has shown that it is a rare form of calcite, a crystal that refracts light in a very unique way. Some experts are now arguing that the Sunstone's legendary magic may be based in science, but it's never been proven in the field. What is it about this particular crystal that makes it so special?
It creates two images of a single ray.
In theory, the Vikings could have prepared the stone by adding an arrow pointing along the width of the crystal, and then partially covering the rest of it to create a wide slit. But because calcite splits light, you'd see two slits on the other side. And so how does that, in theory, help you navigate?
One of the pictures will be fainter, the other will be stronger. If you orientate your crystal in a way that you see them to be equal, then you have a reference from which you can say the sun is that way.
It's a startlingly simple idea. Find the angle where the two double images look the same, and bingo, your arrow is pointing to the hidden sun, even if it's below the horizon. However, you'd need more information than that to truly navigate. The Sunstone potentially could show you the location of the sun, but it can't really show you north, south, east, and west, right?
Yes, if you have a proper working sunstone, then you will need a twilight board, which is a kind of sun compass, and a shadow stick, which can work instead of the shadow, which you will not see.
A twilight board is a sort of sundial, but instead of the sun's shadow showing time, it shows direction. When the sun is hidden, a so-called shadow stick is used instead. Based on the location of the sun as determined by the sunstone, the shadow stick can then be used to calculate direction. Have any twilight boards or sun compasses or shadow sticks ever been found?
There is one artifact which was found about 60 years ago in Greenland. And the reconstructions tell us that it might have been a twilight board.
This artifact may be a clue, a device that worked with the Sunstone. But can it be proven? Has anybody taken a piece of calcite and tried to construct these items and tested them out on the open seas to see if they can be used to navigate?
I have never heard that anybody has actually tested it on the sea.
Incredibly, we could be the first to test this on the water and prove that we can actually use the crystal to navigate. This is a perfect replica of the Oseberg ship that I saw in the Viking Museum.
What's that, Stone?
I said not without a clock.
How dare you?
You have to know what time it is. They're checking the azimuth of the sun with this crystal. Well, azimuth has everything to do with time. If you don't know what time it is, well,
Well, you
okay,
can
continue. Go ahead.
pinpoint it between 0 and 180, right? It could be literally anywhere.
Could be all time or whatever.
Is a masterpiece of historical construction and the perfect vessel to test out whether the Sunstone can be used to navigate. With the sail unfurled, we're underway. The weather is bad. The boat is a design that predates the horse and plow, but this is the moment. Will the Sunstone reveal its mystical qualities, or are we about to be lost at sea? All right.
Stone, could they get their local noon from whenever the sun reaches its zenith, though?
Yeah, but how are you going to figure that out when you're flopping around in a little boat?
That's true. It would be like a rough estimate, especially when you can't see it if you're just using the crystal.
Unless
But
you got a sextant in your hand. I mean, like, okay.
got that rough esty?
Right, here is the
Yeah, I'm sure the Vikings did everything kind of roughly, just winging it there. That's how they were totally superior.
That was the story. They had telescopes to tell time at night, but we couldn't put a telescope on a moving, bobbing ship. They argued that's why we needed the chronometer.
Sunstone. So let's talk about what's been done to the stone here.
You have two slits now. You have to look through this slit, and you will see two images.
I do. When I look through this, I see a double image of the slit on the backside.
Exactly. If you find the position where the two just seems equal, then your arrow will show you which way the sun is. Let's hope it will work.
Right. By holding up the crystal in the haze, the double image of the slit appears. One side darker,
All right, I
one
don't think I get how this
but
is
by
working.
rotating the crystal, they should match. When they do,
It'll make a little more
I don't
sense
understand how
when
this works. Oh,
it'll
okay.
make a little more sense when he does it.
the
Are they
arrow
following
should
in a
point to the sun.
crepuscular ray? Is that what it is?
No, so you just hold it to your zenny, and then you just like look around, and then when the pattern inside the crystal is illuminated equally, that's when the arrow will be pointed at the sun. Or in the direction of the sun, rather, in the sky. So what he does is like you'll take a sweep of the sky coming from east or west or whatever direction, and then you'll do the opposite, and then you'll kind of like make an X, and then you'll just kind of estimate where the thing is. Like he does it here. He's about to get to the actual process. You'll see it.
All right.
You ready?
I'm really excited.
Sunstone, here we come. I scan the sky in an attempt to find the spot where the two images on the far side of the crystal appear the same. The differences are subtle, and I'm not having an easy time making it work. But then, I find it. There.
Okay, remember which way the arrow is showing
The
this.
arrow is pointing this way, so this is telling me, if this is working, that the sun is somewhere this way.
Okay, just look for another point and do the same.
The idea is to do the experiment twice, using the intersection of the two arrow lines to find the exact position of the sun. Try to not drop the sunstone in the sea. There, right there, right there. That's equal.
Now try to estimate the intersection.
Okay? The first estimation was pointing this way, the second estimation was pointing this way.
Okay, so just follow those lines and try to say where the sun is.
The sun should be here.
Just
With the sun possibly located, we break out the twilight.
Stone, I can tell by your laughter I've been duped.
Oh God, we're getting out the high-tech gear now, bro. Check it out.
Bro, we're about to get the Twilight dial out.
Board and shadow stick to take a measurement. I don't really know how to use it, so now I really need your help.
Okay,
Where's
you
Eratosthenes
think the
when you
sun
need him?
should be there, so you basically aim that point at the position of the sun,
Got
which
it.
you have measured with the sunstone.
And then the compass underneath should become accurate.
Yes, that's the idea.
So in order to test that, we need a real compass.
Yes.
You have a real compass?
Yeah.
Let's see how we did here. What do you think?
I think it will work
Yeah,
because
because you made it.
yes, of course.
Balázs takes a bearing with his magnetic compass, something not in use in the Viking Age. The test now is to see how well my compass, which is nothing more than a crystal and a piece of wood, compares. Here, let's line it up. It works! That is unbelievable. The bearings are nearly identical. This is the first successful test on the water that proves the sunstone is real. That's almost a perfect match.
What?
Well, I'm amazed.
North?
No, he's just pointing north. That's where he drew the arrow.
With
The
a
thing's
magnetic-
pointing the other way. What do you mean?
With a magnetic compass, you got a declination chart handy to find where actual north is based on your magnetic reading?
Didn't work at all.
Yeah,
huh?
I don't understand how this works then, because the thing is pointing the other way, and he is aligning where he drew north on his piece of wood with the compass pointing north. Like, aha! I'm like, isn't it the other way? Whatever, fine. I want to see it activate when the
It
sun's
lines up
below the horizon. Sorry.
almost exactly.
It's amazing.
This is a device that potentially could have been in use hundreds of years before the magnetic compass was being used in Europe.
Yes, because if you have no alternative, then, well, it's pretty good.
Viking Sunstone, check.
Maybe we could sail out to Greenland now.
Oh, you think so? You're feeling confident?
Oh, of course.
Okay, to Greenland, guys. Let's go. Let's get this thing in gear. Come on.
Off to Greenland.
I haven't laughed that hard in a while. Thanks, man.
Mm-hmm.
Well, I want to see it when the sun's below the horizon. Like, show me a nighttime shot of you aligning the two lines so that I can.
Yeah, so they
The sun
don't
is.
they don't do the nighttime one, but in this paper they say that they do.
I still don't understand. Like, is it following a crepuscular ray? Is that why it points to where the sun is? Is that what the two lines are doing?
Nah, they're pretending polarization is giving us some kind of matchup of intensity with
Directionality?
respect to incident angle. Yeah.
Yes. Yeah. So did you get a chance to read over this, Stone?
No, I didn't.
Give it a little preliminary.
You gave it to me a couple hours ago.
Yeah, that was my bad. This was what you would call spur of the moment or last minute.
Yeah, I'd say. Yeah.
So anyway, we're gonna go through it. Anyway, this paper is supposed to be kind of academically going through the concept of what Stone was just putting down, using the angle of incidence of the polarization to determine the direction of which the sun is at, using a biorefringent crystal. So the crystal that has the double refraction thing. So we're going to go ahead and go through and read this. So this is the Sunstone and Polarized Skylight, Ancient Viking Navigational Tools. Although the polarization of light was discovered at the beginning of the 19th century, the Vikings could have used the polarized light around the 10th century in their navigation to America using the Sunstone, evoked in the Icelandic sagas. Indeed, the birefringence of the Icelandic spar calcite, a common crystal in Scandinavia, permits a simple observation of the axis of polarization of the skylight at zenith. From this, it is possible to guess the azimuth of the hidden sun below the horizon, for instance. The high sensitivity of the differential method provided by ordinary and extraordinary beams of calcite at its so-called isotropy point is about 2 orders higher than that of the best dichroic polarizers, and permits dichroic, thank you. The best dichroic polarizers, and permits to reach an accuracy of plus or minus 1 degree for the sun azimuth at sunrise and sunset. Unfortunately, due to the relative fragility of the calcite, only the so-called Alderney crystal was discovered on the board of the 16th century ship, or 16th ship. Curiously, beyond its use as a sunstone by the Vikings during these last millennia, calcite has led the discovery of the polarization of light itself by Malus, and is currently being used to detect atmospheres of exoplanets. That's my favorite kind of use of light polarization, detecting the atmosphere of exoplanets. Moreover, the differential method of light polarization detection is widely used in the animal world. So, introduction. It has been well established. It is a well established fact that the Vikings voyaged from the coast of Norway and perhaps from the present day, and sailed to Iceland and continued on to Greenland and reached America around year 1000, as confirmed by the discovery of the archaeological site of El Ansi X or Ox.
Oh, Meadow.
Oh, thank you. It sounds nice when you say it. Lans on. Do it again.
Lance O Meadow.
Lons O Meadow, thank you, in Newfoundland in 1960. The Vikings were outstanding navigators who used their navigation technology to explore the North Atlantic as well as Russia. These skilled navigators sailed the seas for approximately 300 years, 750 to 1050 CE. Figure 1 shows their main navigation routes. It should be noted that during this period, the Vikings had no knowledge of magnetic compasses. Even though the magnetic compass was invented by the Chinese as early as the Han Dynasty in 206 BCE, the first recorded use of Europeans using it dates back to the end of the 12th century. This brings into the question how the Vikings successfully navigated in the open sea. Although many books have been written about their voyages, there is not much information on their navigational methods. There are a few relics elucidating to their navigational techniques, particularly when they sailed thousands of kilometers of open water between Norway and America. In ancient times, navigation was more of an art than a science. The navigator had to apply multifaceted knowledge to the problem of guiding a ship from its origin to its destination. At the high latitudes of 61 degrees north, these accomplished navigators could use the sun and the stars, and also the directions of the wind and the waves and the swell. 1 second, gonna get some water. However, during the best navigation seasons from May to September, these northern latitudes experience long days and short nights, and consequently, the stars are only visible for a few hours. So the sun was the more important celestial object in practice. When the sun was directly observable, the Vikings used horizon boards and sundials like wooden disc found in 1948 in Unatork. Yeah, that place in Greenland. Unfortunately, when the sun was hidden by the clouds or below the horizon, these instruments are not suitable. Moreover, these high latitudes, twilight can last hours. In such situations, 2 Viking sagas of the 13th century included the Icelandic hero Sigrid's saga, hint that the sailors used a solar steed, i.e. a crystal called a sunstone. The saga describes how during the cloudy weather, King Olaf consulted Sigrid on the location of the sunstone. To check Sigrid's answer, Olaf grabbed the sunstone and looked to the sky and saw from where the light came, from where he guessed the position of the invisible sun. In the Hafran's saga, it says, whether it was sick or stormy, or the weather was sick and stormy, the king looked about and saw no blue sky. Then the king took the sunstone and held it up, and there he saw the sunbeam from the stone. The link between the enigmatic sunstone and the polarization of light was first suggested by Ramsco. Ramsco. All right, here's the map of where they were navigating all around using their sunstones and wooden dials, allegedly. All right. Figure 1, the main Viking sailor route connecting, for instance, Norway to the meadows in Canada, taken from the Cultural Atlas of the Viking World, reused with the permission of James Graham Campbell. Thank you. Thanks, James. All right, sky polarization and the naked eye observations. The polarization of skylight. The first observation of the polarization of skylight was performed by Arago in 1809, only a year after Malus coined the word polarization. However, the first quantitative treatment of the scattering of light by gases, such as those in the atmosphere, to examine this polarization was only proposed in 1871 by Rayleigh. In this theory, Rayleigh developed his famous inverse fourth power of the wavelength law, which explained the blueness of the sky and showed that the main source of polarization in the sky results from scattering by atmospheric molecules, oxygen, nitrogen, etc. Further developments and extensions have provided us with a complete E-vector pattern of the celestial hemisphere. For Viking navigation, the simple observation of the polarization of the skylight at zenith is sufficient to deduce the azimuth of the hidden sun at 90 degrees from its main axis of a partially linear polarized light. For instance, when the sun is below the horizon. Ramsku's pioneering suggestion. In 1967, Thorkild Ramsku, a Danish archaeologist, realized that the Vikings could have used polarization of the skylight when the sun is hidden by the clouds or was below the horizon. The hypothesis that the Vikings could have used polarized light for navigation was due to Ramsco's knowledge of Scandinavian air systems and trans-Arctic pilots' use of Polaroid-based instruments called a twilight compass or a Kolsman sky compass to determine the sun's location. Therefore, he proposed that a local mineral might have been employed as a polarizer by the Vikings in a similar way. A skilled navigator could easily surmise the implication for the use just by gazing at the zenith through the material and the sun, i.e., through the sunstone, and turning in various directions. Ramsco suggested that the corridite, corridorite, thank you, a crystal which turned from yellow to dark blue whenever its natural molecular alignment was held at a right angle to the plane of polarized light from the sun, could have been used as a natural crystal that acted as a Polaroid filter. Let's see, there's a diagram here. So we got our sunlight, got our atmosphere, got our 90-degree ocular there. The scheme of Rayleigh scattering, the unpolarized sunlight becomes linearly polarized when it's scattered by the atmosphere, noted by O2 and the N2 molecules. The direction of the polarization of the scattering is at 90 degrees from the sun's direction. Very cool. All right, so he's suggesting that local minerals could be the Polaroid filter there. He also tested other minerals like tourmaline and Icelandic spar. For him, all these crystals could work as polarizers. This reasoning is based on polarizers being followed by many authors, given by the citations here. However, the weakness of the polarimetric method has been emphasized by Rumsland and Beckman. Indeed, as we will see later, the sensitivity of the polarizer method linked in the common use of Malice's law remain too low for many situations, leading to poor accuracy of the sun's zenith. Section 2.3, the degree of polarization of the skylight. The partially polarized skylight at zenith can be characterized by its degree of polarization by rho equals I max minus I min over I max plus I min, where I max and I min represent the intensities passing through through a perfect polarizer oriented successively along two axes schemized in figure 2. This parameter varies from 0 corresponding to unpolarized natural light to 1 for totally linear polarized light. The value of the degree of polarization of light at the zenith depends on many parameters like the time of day, the clarity of light. The low values of rho of 0.02 being less than rho or rho being less than 0.2 correspond rather to cloudy skies, while high values of rho be equal to or greater than 0.6 correspond to clear skies. Figure 3 shows the typical measurements of this degree of polarization, which is crucial for its use as a navigational tool. In Figure 3 alpha, the skylight corresponds to a rather clear day that is detected through a rotating polarizer. In this case, rho is equal to 0.6, with the values I max and I min measured to the right of the figure. Note that this partially polarized light can be completely depolarized by interposing a calcite birefringent crystal with its optical axis orientated at 45 degrees from the main axis of the incident partially polarized light. As shown on the right of figure 3, the depolarization of light by the calcite crystal is complete in the case of rho equals 0. Section 2.4, the polarization sense of the human and the naked eye observations. Although the human eye is essentially sensitive to the two scalar characteristics characterizing. Let me start over. Although the human eye is essentially sensitive to the two scalar characterizing a light beam, i.e., its intensity and its wave frequency, its color, the physicist Wilhelm Karl Ritter von Hadner,
That's Ritter von Heidinger.
Heidinger, thank you. Your boy Heidinger showed as early as 1844 that they were able to detect the vectorial nature of light, i.e., its polarization, with the naked eye. When a polarized beam of white light falls on the foval cone mosaic, a blue-yellow propeller pattern can be observed, the so-called Heidinger's brush. To observe Heidinger's brush, the easiest way one has to look at a bright sheet of paper uniformly illuminated throughout a sheet of Polaroid. Rotate the polarizer and gaze at the paper. You will eventually notice small colored patterns at the center of your visual field rotating the Polaroid sheet, or rotating with the Polaroid sheet. The yellow brush is orientated perpendicular to this transmission axis of the polarizer, and the blue brush is parallel to the transmission axis. With the naked eye, when the sun is near the horizon, if you look straight up towards the zenith with the sky free from haze, you can observe the brushes when you rotate your head and deduce the sun's zenith. What? In addition to the approximate 3-second fading time due to the neuroadaptation measuring the stationary stimulus, these brushes exhibit an extra short creating and erasing time of about 0.1 seconds when a dynamical stimulus like a rapid polarization switch is used in citation 21. Moreover, as Heidinger's brushes are only induced by the blue part of the light spectrum, the human eye is able to act simultaneously as a monochromator, detecting only the blue light as a differential analyzer. Direct naked eye detection of the optical activity of the chiral molecules of the Faraday magneto-optical rotation of linearly polarized light in white light is possible and have been demonstrated, providing direct access to reciprocal and non-reciprocal characteristics of these fundamental effects. And here's the diagram for that. All right. Indeed, after a forward pass through the material, a reflection, and a second backward trip through the material, the naked eye is able to see that the whole rotation is doubled for the Faraday non-reciprocal effect, but is canceled for the reciprocal optical activity. The short creating and erasing time of the Heidinger brushes suggests the first detection of polarizing the skylight using calcite. By comparing two different successive patterns, namely those observable with polarized and non-polarized states of skylight as shown in figure 4. Gazing at the sky at zenith through a calcite crystal at its isotropy point with the expolarized light in figure 4 alpha is completely depolarized, and no Heidinger pattern is observable in the plane of the eye fova. By contrast, if we remove the crystal rapidly, the polarized electric field E of the skylight aligned along the x-axis induces Heidinger's brush on the fova as shown in the bottom of figure 4b. Thanks to the short 0.1 second reading and erasing time, one may alternatively interpose the depolarizing crystal in line of gaze and rapidly move it so that it's easy to observe the successively the no pattern image when the pattern image is shown in the bottom of figure 4. The yellow brush is perpendicular to the scattered electric field of the skylight and gives directly the direction of the sun. To estimate the accuracy that can be obtained by such observation, we have compared the bearings made by different observers using solar locator devices schemized in figure 4 with the sustainability of the sun locator device, the azimuth of the sun can be determined with an accuracy of about plus or minus 5 degrees. Aboard a boat, the precision is probably reduced, but could have provided the Vikings with the first estimation of a boat course. However, this method requires a very clear sky at zenith. Note here that the calcite crystal works as a depolarizer for the linearly polarized light impining on the entry face of the crystal.
Yeah, that's impinging.
Impinging, okay. Yeah, I was going to say, I don't quite know if that's impinging. So linearly polarized light impinging. What does that mean when it's just hitting it dead on?
Kind of sneaking in the door of, if you will.
Okay. Although the isotropy point of the calcite permits the first observation of the sun direction thanks to our polarized sense based on the Heidinger's brush, equipping the crystal with a simple screen and a small aperture suggests a more powerful differential observation, allowing the direction of the sun's azimuth with higher accuracy and for weaker degrees of polarization of skylight. Section 3, comparative analysis for dichroic and dichroic, thank you. And birefringent crystals to detect the direction of the given linear polarized light. The usual polarimetric methods consist in a rotating polarizer so as to reach the minimum for the transmitted intensity I sub t following the so-called Malice's law, i.e. I sub t is equal to I cosine squared of alpha, where I is the incident intensity of the polarized light and alpha is the angle between the transmission axis and the polarizer and the incident of the electric field direction. For alpha equals 90 degrees, the transmitted light equals 0. The cordite suggested by Ramscu, for instance, works as a modern Polaroid sheet. This material is dichroic, i.e. it absorbs the light along one axis while it transmits light orthogonal along the orthogonal axis. As a polarizer, it allows one to work with a black background, but determining the crossing point alpha equals 90 is not as precise as seen later. Let us now consider the case of a birefringent crystal like calcite, which is not dichroic, being colorless and completely transparent in the visible part of the spectrum. Calcite crystals are also common in Iceland and Scandinavia. Due to their complete transparency, such crystals can never work as a polarized sheet. For calcite, for instance, and incident-wide unpolarized beams remain unchanged at the output. A polarized beam is even completely depolarized when the crystal is oriented at its isotropy point. Figures 3b and 4 alpha there will show what that looks like. However, paradoxically, the same calcite crystal can offer a powerful method to detect a given state of linearly polarized light when using narrow beams. Indeed, when equipped with a screen with a small aperture, as shown in figure 5 alpha, the unpolarized sunbeam passing through the aperture is split into two distinct beams, giving two images of the aperture at the crystal output with an equal irradiance. This double refraction inside the crystal was discovered by Bartholomew's. Yeah, that
Bartholomew's. Yeah.
Nice, my boy, Bartholomew's in 1669. To investigate the potential of double refraction in laser physics, it was necessary to introduce a 4x4 Jones matrix. The old 4x4 Jones matrix. Here, let us recall the main properties of the calcite schematized in figure B4 or 5b. For the rhombic crystal with an edge equal to a length of its optic axis AG joins the two blunt corners of the rhombohedron at 102 degrees in angle, at three 102 degree angles. The principal section where most phenomena occur, shadowed in the blue, contain the optical axis of the crystal. The walk-off distance delta is the section spatially that's separated by ordinary and the extraordinary beams at the exit of the crystal shown in figure 5 alpha. Typically, with the calcite crystal thickness of E equals 3 centimeters, the spatial separation delta is given by delta equals E tangent gamma, where gamma is the angular separation between the two beams inside the crystal, and this is about 3 millimeters. With the typical images refer to the Bartholonolists, I'll never get that right again, are observed when they simply cover a sentence in the printed text with a calcite crystal shown in figure 5C. The two gray images are shafted along the principal section containing the optical axis. Note that, as shown in figure 5C, while the ordinary beam obeys the usual Snell's-Descartes law, or Descartes law.
Snell-Descartes.
Yeah, Descartes. The Snell-Descartes law. How's that? The Descartes.
Snell-Descartes.
Descartes. The Snell-Descartes law. The extraordinary beam does not obey this law. To visualize the violation of the refraction law by the extraordinary beam inside the crystal, we have chosen a dark blue laser to excite the bluish phosphorescence of the residual ion impurities in the crystal in figure 6. It is worthwhile noting that this anomalous refraction in calcite is a particular case of birefringent crystal that comes about when the axis of asymmetric molecules in the crystal are not parallel with the face of the crystal. Note. Here we got some schematics here. We'll take a little gandy here. All right.
So judging by the looks of that diagram right in the center, that 0.6 meter by 2.4 meter inset with the eye looking straight up, the guy in that video you first showed was not even using it correctly, dude. He was angled toward the horizon,
Right.
looking for change. And that's totally orthogonal to the process of polarization overhead at your zenith, which is where the measurement is being taken from. Oh, we got it! We got it! It's just like the compass. Look!
Well, I'm glad some lads took some seriousness to it to properly do it. Because, yeah, that YouTube video definitely, it might work, but like not on the principles that they showed, huh?
Well, they dressed up like Vikings, so it had to be real. The costumes they had were all the money went, obviously. So
You know what hooked me? It was the costumes and that one guy's beard. He looked like he was about to go on a Viking raid, bro.
I think that was actually part of the control elements in the experiment. The calcite may not actually work unless you're dressed like an old Viking.
Dude, it only responds to Vikings. That makes sense.
If you're the king, you have to wear a shitty gray toque.
Well, the costumes did lend like an air of authenticity, you know.
All of YouTube agrees, so.
Nice. As long as we can form a consensus, we can override science or whatever. All right. Note. Well, actually, let's read the description here. Figure 4. Alpha, gazing at the blue patch of the sky at the zenith with the sun near the horizon, simply through the calcite crystal without any screen, oriented at the isotropy point K, acting as the perfect depolarizer. No pattern is observed in the fova. Am I saying that right? Is that fove or fova? Fove?
I think it's fovea.
Fovea. Okay, fovea. When the crystal is rapidly moved, a Heidinger's polarization pattern appears on the fovea. See the bottom right. The yellowish brush directly gives the sun's direction, as the entodic pattern of the fovea cannot be photographed. The scheme here is simulated. The scheme of the sun locator device used in the experiment is shown in the inset. Figures from 28 reused with permission from the Royal Society. Shout out to the Royal Society. Shout out to the lads, dude, helping us out. So yeah, there we go.
Someday we'll have a prez and they won't be part of it, but it's not today.
So someday there will be a scientific conclusion completely independent of the Royal Society. we will find it. We will keep searching. All right, such an anomalous refraction has yet to have been discovered in the metamaterials. That was following. Note that such anomalous refraction has also been recently been discovered in the metamaterials. Okay, there we go. Okay, when using unpolarized light, as shown in Figure 5a and b, the irradiance of the two images are always equal, whatever the orientation of the crystal. Although the two beams are orthogonally polarized. By contrast, using the incident polarized light, as illustrated in Figure 7, opens up new possibilities. As recalled previously, when a dichroic polarizer is used to analyze this linearly polarized light, the transmitted light, governed by Mal's law, is represented theoretically in Figure 7a when a polarizer is rotated. Of course, the black background is reached when the working point of the working point, which corresponds to alpha equals 90 degrees, but the variations of the transmitted light shows 0 value for alpha equaling 90 degrees and remain weak around this working point, as shown by the derivative of di over d alpha as represented in Figure 7 alpha. By contrast, this derivative is the maximum for an angle equaling 45 degrees, which is precisely corresponds to the working point of the bifringent crystal. Indeed, the incident linearly polarized light is then at 45 degrees. So here we got some schematics.
So really quick on the other schematic, it looks like when they're pointing straight up, as Stone was highlighting, it looks like they're just right there. They're not testing it in the way that they did out at sea. They're just demonstrating the example of how they set up their test for the birefringent properties of the stone, or of the material, because it's not the actual stone. I don't know what material they're using right here, but it doesn't look like they're like intending to claim here with this diagram you're showing that this is us testing it out at sea by looking at the horizon or by looking at the sun on a cloudy day. It looks like they're showing like their setup as to how they were testing it in the lab to further and research its biorefringent properties. Am I seeing that correctly?
The way
It
I'm
doesn't
reading
look
it,
like a real.
yeah, the way I'm reading it, it looks like they were using it to measure the sun, like angles, or the direction to it, the azimuth to it.
Oh, okay. Where is the sun in there?
Well, in here they're talking about when you do this, the pattern produced inside gives you the direction of the sun, so they'd have to be referencing skylight for that to happen.
They're looking straight up.
Yeah.
So they're looking straight up at the sun. This is when the sun's over their head. Is that what?
No. The sun is off in some direction, and they're just looking straight up at their zenith, and through the polarization that's going on, this pattern is produced, and this pattern is in the direction of where the sun is actually at.
Okay, I was trying to understand what it is that they were, what I was looking at there. I get it now. So they're looking up through the crystal.
Yep. We got some schematics here. We got our unpolarized sunbeam. Now that refracts the image through. B, unpolarized light. Screen.
We're using a laser there, I see.
Okay. Yeah. A giant laser. All right, Figure 5. A, with an unpolarized sunbeam impinging on the calcite crystal equipped with an opaque screen with a small square hole, the photo shows the two images with equal intensities, whatever the crystal orientation is. B is a scheme of a narrow, unpolarized light beam traversing the calcite principal section. The blunt corners, where all the faces equal 102 degrees, obtuse angles are marked by the two yellow marks. For a crystal with the edge of equal length, the optic axis joins these two blunt corners. C, the typical double image of a sentence printed on text. The ordinary image is fixed with the upper extraordinary image in the image is shifted and can rotate from the optic axis of the calcite crystal. Oh, whoops, that's actually okay. So this is for the description. This is following this.
Then at 45 degrees, blobby blobby crystal.
Yep, the incident linearly polarized light is then at 45 degrees from the optic axis of the calcite crystal. According to Malice's law, applied simultaneously to the beams, the ordinary and extraordinary intensities through the bifringent crystal can be written when the crystal is rotated, given by equation 1 and equation 2. So the contrast between the ordinary and extraordinary beams is the delta L over I is equal to all that, which is equal to rho, given the absolute value of the cosine times 2 alpha, will exhibit the sharp variations of both sides of the working point, as shown theoretically in figure 7b and experimentally in figure 8. We can then compare quantitatively the efficiency of the polarizer and the depolarizer around their 90 and 45 degree working points, respectively. The results are shown in figure 7c. The detected signal itself is more than 10 times larger for the bifringent crystal than the best dichloric crystal. The twofold application of Mau's law around the isotropy point, where the intensity of the ordinary and extraordinary beams are equal to their opposites, relative variation maxima, permits the simple solution for plausible Viking navigation using the polarization of skylight at the zenith. This overcomes the previously mentioned reservations concerning the polarizers of Beckman and what was that other gentleman's name? I got their papers here. The Rose stunned. All right. Moreover, another important point concerns the comparison of the respective sensitivities obtained with the dichoric polarizers and the bifringent crystal. Indeed, when adjusting the cross polarization detection with the dichoric polarizer, the observer has to compare the irradiance of successive images while he uses the bifringent crystal. He has to appreciate the contrast between two simultaneous images as shown in figure 8. The physiological sensitivity to the human eye to contrast between two simultaneous images is very high and known to be 1% or less. The sensitivity of the naked eye to contrast has recently made it possible to detect the extra layer of atoms on one part of a plate, which includes a small increase of 2.3% opacity. So overall, the performance of the bifringent crystal is about 2 orders of magnitude better than that of the usual polarizer. Indeed, as shown in figure 7c, for instance, for the rotation of 5 degrees, the sensitivity of the depolarizer is 20 times greater than that of the usual polarizer. Furthermore, comparing the irradiance of the two simultaneous images with the depolarizer is about 5 times more precise than comparing the irradiance of the two successive images through a usual polarizer. Here we got our graphs and schematics there. Figure 7, the linearly polarized light comparative methods used for Mau's law for the two working points corresponding to the polarizer and depolarizer. The Mau's law with its two possible working points and its derivative. B, the theoretical contrast on both sides of the 45-degree isotropy point of the calcite. C, the comparative signal intensities for the polarizers and depolarizers methods around their respective working points. Figures from citation 23 reused with permission from the Royal Lads. Right. So thanks to the Binet principle,
Babinet.
Binet, is that
Babinet.
Babinet? Thanks to the Babinet principle, similar results can be obtained for the complementary screen illustrated in Figure 9. Here, if instead the whole of the opaque screen, as shown in Figure 9, we use the opaque dot on the incoming face of the crystal, and we will observe the we will observe two half intensity dots. This configuration used initially with Bartholomew's. Oops, someone's hot mic in there. Hot mic and lad. Also, that's doesn't make any sense. All right. By the Bartholomew or whatever. Anyway, has
Bartholomeus.
Dude, it gets me every time. Bartholomeus. Bartholinus.
Bartholine.
Score.
Phew, it can't be that easy. My brain's reading it completely differently. All right, this configuration used initially by Bartholomew's has been followed by Ramsco and Carlson. However, as shown in Figure 9b, the geometry of the observer will receive all light impinging on the crystal. So following Weber's law, the eye has to adapt to the background illumination to be able to distinguish the objects in the background, taking into account the threshold it increases with the background luminance, which is approximately proportional to the background light level. Moreover, this configuration, all the defects in the crystalline are illuminated by the incident light and add unpolarized stray light to the ordinary and extraordinary gray dots. By contrast, the use of an opaque screen with a small aperture, lightly smaller screen, and the spatial separation of the two beams minimizes this drawback. All right, we got some more schemes here. Got Figure 9. Scheme the ordinary and extraordinary beams in the principal section of the isotropy point 45 degrees. For the screen with the square hole represented by AB on the opaque screen, where AB is equal to alpha, which is equal to 45 degrees, is here smaller than the walk-off distance delta. The output of the calcite crystal in the two images have equal intensities. B, the scheme of the complementary screen, i.e. the dark dot. Section 4. Experimental results of the Iceland spar. A typical experimental results is shown in Figure 10a. When the Iceland spar is pointed towards the zenith and rotated back and forth around its isotropy point, the experiment was performed with a clear sky corresponding to a degree of polarization of rho equaling 0.6, the sun being near the horizon. At the isotropy point of 45 degrees, the irradiance of the two images are quasi-equal. For around an angle of 35 degrees, the ordinary image irradiance is greater than the extraordinary one, but the result is reversed for a degree of, or for an angle of 55 degrees, in agreement with the theoretical curves produced earlier by the graphs that we scrolled past. The corresponding density profiles shown in Figure 10b confirm that the irradiance of the two images are easily discriminated in this case. Here, the density profiles show that the contrast of 18% can be obtained by the rotation of the calcite crystal of 10 degrees. Hence, a precision of plus or minus 1 degree can be reached, as the sensitivity of the human eye contrast can be as low as 1%. This high sensitivity to contrast of the human eye permits to perform polarization observations for many types of situations. Of course, as the contrast delta I over I is proportional to the degree of polarization of the sky light rho, this parameter plays a crucial role. Figure 11 shows the theoretical curves of the value rho varying from rho equaling 0.06 to rho equaling 0.6, corresponding to different sky conditions encountered in navigation. Note that the V-shaped curves linked in the contrast variations are particularly well suited for determining the isotropy point. To demonstrate the high efficiency of the differential method with a hole in the opaque screen, for quite low degrees of polarization, we compare them in figure 12 to the theoretical signals for the orientations of the crystal corresponding with experimental measurement. Here, rho is equal to 0.08, which corresponds to a cloudy sky. The agreement remains quite good even when the back and forth rotations of the crystal are reduced around the isotropy point at 45 degrees. Note, for a rotation of about plus or minus 10 degrees around 45 degrees, the contrast remains as high as 3%, i.e., clearly above the limit fixed by the 1% sensitivity of the human eye that it has to contrast. So to have a bearing of the sun's azimuth remains possible for low degrees of polarization. The inset of figure 12 shows the Iceland spar used in this experiment, similar to the ones that the Vikings could have employed as a sunstone. The V-shaped signals provide us with a precise theoretical and experimental method to determine the isotropy point, but we have to calibrate the crystal itself versus its own optic axis so as to point with high accuracy to the true bearing of the sun. The calibration can be performed at twilight, a day with a clear sky when the sun is still observable at the horizon, equalizing the ordinary and extraordinary intensities at the isotropy points. We have just to fix the arrow as shown in the inset of figure 12, the direction of the visible sun. The pointer is then fixed exactly at 45 degrees of the optic axis. Fixing the pointer along one or the other edge of the crystal is done after the usual polarizer. This leads to an error of plus 6 degrees on the edge and minus 6 degrees on the other edge, losing the accuracy of the method. With the correct calibration, the sun direction is found at the 45 degree from the optic axis of the crystal. A possible Viking Sunstone compass prototype is shown in figure 13. The Iceland spar with its screen can be rotated to equalize the two images' iridescences. Of course, the yellow arrow being at 45 from the optic axis. We have 4 possible solutions for equalizing two intensities: 0 degrees, 90 degrees, 180, and 270, negative 90 degrees, and 0. Oh, which is just be that. Is the true bearing of the sun, as shown in figure 13. It is easy to identify the ordinary and extraordinary images, which are labeled by the small patch on the apparatus. Indeed, when the crystal is rotated, the mobile image is the extraordinary one. Now, to simplify to identifying unambiguously the true solution for the 0 degree solution, the true bearing. When one rotates the compass in the clockwise direction, the intensity of the extraordinary image increases as depicted in figure 8. By contrast, the 90 degrees for the plus 90 degree solutions, it is the intensity of the ordinary image which increases when the compass is rotated in the same clockwise direction. The plus 180 degree solution can be determined by either using the sky luminosity differences between 0 and 180 degrees in direction, or observing the natural elements like the wind and the wave direction. Knowing the time of day permits us to deduce the north direction as the passage of time is entirely predictable and can be estimated fairly accurately by the body's internal clock. To test the potentiality of this Viking Sunstone compass, we have tried to follow the azimuth of the sun passing below the horizon at twilight. The measurements can be performed after sunset till the appearance of the first stars. The agreement between the experiment and theoretical values is still very good, justifying the accuracy of the calibration. This simple differential method could have been powerful help for the Vikings for their navigation in open sea without requiring any knowledge of polarization. One may wonder if such observations by the Vikings is plausible. Section 5, the differential sunstone method for detecting polarized light. 5.1. The Iceland spar in the introduction of the polarized light by Malus. The word polarization was first coined by Malus after his famous experiment in 1808. Malus was familiar with the double refraction of calcite. One evening from his home in the stone, hit it with the French.
The Rue d'Enfer.
The Rue d'Enfer sounds. The omelette de fromage. Is that about where it was at?
That's Steve Martin. Excellent. Excellent.
All right, let's see here. So, so this place in Paris, Malus examined the sunlight reflected from the window of the Palace of Luxembourg, just over 1 kilometer away. Looking through the Iceland spar, he expected to see 2 images of equal brightness, but instead found that if he rotated the crystal around the line of sight, each image from the window was dimmed in turn every 90 degrees. He realized that the first polarization phenomenon was not inherent of the crystal media itself, but an intrinsic property of the light reflected by the window. Curiously, Malus used the same differential method to discover the polarization of light reflected from the window as one of the Vikings could have used it to determine the azimuth of the sun using the polarization of the skylight without any knowledge of the phenomenon. Note that this remarkable discovery of Malus led to the fundamental introduction of Young and Fresnel and the transverse nature of electromagnetic waves. Shout out to our boy Young and Fresnel, not to be confused with Young Fresnel. That's a different person. Section 5.2, the Iceland spar to detect the atmosphere of exoplanets. Yeah. All right, today, the detection of the atmosphere and exoplanets. Oh, man. All right. Today, the detection of the atmosphere and exoplanets has become a crucial point of research of plausible extraterrestrial life. Curiously, in recent successful detections of very weak beams of polarized light scattered from the atmosphere of Earth-like planets, such as HD 189733b, the authors, in citation 39, used the ordinary and extraordinary beams of the Iceland spar with a differential method, but with a screen being located after the crystal so as to eliminate the stray polarization effects arising from the Earth's atmosphere itself. Section 5.3, the differential method in the animal world. I'm so glad that this method was real quick.
Wait a minute. Wait a minute here. What's this thing we had to wait until night? No, because the polarization only works when the sun is allegedly out or just below the horizon.
Well, yeah, just as you were just able to see the stars.
Yeah, that's some silly shit. Anyways, let's go.
5.3, the differential method in the animal world. Since the experiments of von Frisch, yeah. Von Frisch with bees, many animals have been shown to be directly sensitive to polarized Rayleigh scattering UV and blue light of the sky, and to use the spatially polarized light in their surroundings for navigational and signaling purposes. In the case of compound eyes with orthogonal microvilli, these animals also use similar differential methods for detection of polarized light, of course, without any knowledge of polarization itself. For instance, in figure 16, we have taken the case of a spider, from citation 37, which has on its back 2 eyes dedicated to the polarization detection. There is no separating crystal to have ordinary and extraordinary beams, but the separated eyes. However, the parallelism can be directly established between the example of the spider and the human eye behind the calcite equipped with an aperture. It has also been suggested that migrating birds can use polarization to aid in navigation. Indeed, for migratory songbirds, the multiple compass systems have been recalibrated. No, wait, that's not. Is that following the same? Yeah, multiple compasses systems have been recalibrated, namely at sunrise and sunset, when conflicting with the direction information when conflicting with directional information. For example, when the magnetic declination changes at especially high latitudes. Gotta watch out for those high latitude changes.
That little bit I mentioned when they were back on the boat about the declination chart seems to be relevant now.
It does have some importance to it. Section 6. Search for the Viking Sunstone and the Alderney crystal. The search for the Sunstone could have done either in ancient Viking settlements and shipwrecks or in ancient Viking burials. However, it is worth noting that the calcite crystals are rather fragile, both from mechanical and chemical points of view. First, in recent excavation in Iceland, the small calcite fragments was discovered in the Viking settlement, giving evidence that some people in the Viking age may have used the Iceland spar crystals. Yep. More importantly, the large calcite crystal, a large calcite crystal has been excavated on board a 16th century shipwreck. To the best of our knowledge, it is the sole calcite crystal found on board an ancient ship. Although the ship went down off the coast of Alderney, the 5 centuries after the Viking Age, the calcite crystal would have been used for navigational purposes as discussed below. Indeed, in figure 17 shows the Alderney crystal found exactly at the same location as a pair of navigation dividers. Of course, since the magnetic compass was introduced in the 13th century Europe, this ship was equipped with a magnetic compass. Although easy to use magnetic compass was not always reliable, as most of the magnetic phenomenon were not well understood in the 16th century. Indeed, one had to wait for Gilbert at the beginning of the 17th century to understand the main point of magnetism, points of magnetism phenomena. If the time was correctly known, the calcite sunstone could make it possible to check and recalibrate the magnetic information, similarly to how the migratory birds would do it in citation 38. So we have figure 17, a photo of the calcite crystal and the pair of navigation dividers discovered on board of the ship Shank and 4 November 1592 off the coast of Alderney in England, off the English Channel. A few years after the famous Battle of the Spanish Invincible Armada. The crystal shown near one of the cannons excavated from the same Elizabethan wreck may have been the only known example of the sunstone found aboard an ancient ship reused with the permission of the Alderney Museum. All right. We were at the birds. Okay. Here, the magnetic compass on board of the ship can be perturbed for various reasons, such as the presence of the cannons, the optical compass giving the absolute reference many used when the sun was hidden. With the Alderney-like crystal, an accuracy of plus or minus 1 degree can be reached at sunrise and sunset, as shown in figure 14b. Although the use of the Sunstone navigation instrument has not come to attention of natural philosophers, it is worthwhile to note that the sunstones have been mentioned in the inventories of the churches in cloisters in the 14th and 15th centuries. From an archaeological point of view, the Alderney crystal brings further indication for searching for possible sunstones in Viking shipwrecks. Indeed, as shown in figure 18, when the calcite crystal has been immersed for centuries in salt water or seawater, many chemicals and mechanical effects occur, modifying the optical properties. Figures 17 and 18 show that the Alderney crystal has lost its transparency but kept its rhomboidal rhomboidahedral geometry with its specific 102 and 78 degree angles, respectively. The relative measure of concentration of Mg2 plus traces on
Magnesium.
magnesium. Okay. The concentration of magnesium traces on the an ion are common in seawater. Using inductively coupled plasma atom emission spectroscopy for the Alderney crystal compared to the freshly collected calcite as shown in figure 19, the magnesium concentration in the Alderney that's so funny that they're like, we're not going to tell you it's magnesium. We're going to use this. If you don't know what this is, you're going to be real confused. All right.
If you don't know what that is, you're not allowed to read this paper. Just ask PhD Tony.
The magnesium concentration in the Alderney crystal has increased by a factor of 8, as shown by the emission spectra around 279.5 nanometers, reaching 2,000 parts per millimeter. As we got another one, Stone. They think they're clever here.
Calcium.
Alan,
Calcium.
that's 2,000 parts per million.
Oh,
And
2,000.
that's calcium.
2,000 parts per million. Thank you. What did I say? Millimeter?
Yes. Yeah.
Oh, my bad. I was on autopilot.
Interesting unit of measurement.
Thank you. Which one was this? This is calcium?
Yeah.
So as the calcium ion has a stronger diameter, 0.1 nanometers, the magnesium ion, 0.07 nanometers, the crystalline structure of the calcite on the surface is known to be slightly compressed, thus reducing the transparency, but increasing the insolubility and strengthening the crystal. This explains the good conversion, or the good conversion of the rhombohedral geometry. Moreover, the sand debris.
Okay. Oh, 2 in a row, Alan. That's the conservation of rhombohedral geometry.
Did I not say conservation of rhombohedral?
It was a good try.
What did I? Okay, the conservation of rhombohedral geometry. Moreover, sand abrasions alters the crystal by inducing roughness on its surface. Both phenomenon inevitably reduce the transparency of the calcite crystal, but the nice preservation of the rhombohedral crystal may be of interest to archaeologists in the future, excavations. Another possibility to find sunstones could be the Viking burials, Viking ship burials, where many of the artifacts have been discovered. Unfortunately, calcite has a tendency to be fractured along its structural planes when heated. Figures 20a show the typical calcite crystal breaks when heated at 250 degrees Celsius, resulting in small rhombohedrons, little baby rhomboids. All right. However, as shown in figure 20b, the fragments keep their specific 102 and 78 degree angles. Curiously, the relative fragility of the calcite has played a crucial role in the development of crystallography. Indeed, in 1781, the French priest and mineralogist René Justhuet. Is that it, Stone?
René Justhuet?
René Justhuet. A fortunate accident when he dropped a piece of calcite and broke it into a small fragment with the figure shown in 20c. He noticed the calcite fragment broke along the straight lines that met at constant angles. Hua, who is often known as the father of crystallography, introduced then the famous unit cell and showed that the crystals are solid, which are ordered at the microscopic level. Although thermal crystal heating plays a role and impacts the calcite in electron don't tell me. Microscopy. Thank you. Microscopy photo in figure 20c shows that it should be possible to find the specific fragments of calcite in the Viking burial ships. The Alderney crystal and the recent findings of calcite fragments in the Hofstadter hope and lend for the discovery of the other crystal fragments in the different archaeological Viking sites and shipwrecks explored in many countries, namely Scotland, Ireland, Iceland, Greenland, and Scandinavia. All right, we got some various images of the before and after heating. Figure 20, photo of the 5 by 3.5 by 1.5 centimeter crystal before and after the heating. All right. Section 7, other aspects of Viking navigation and conclusion. The thesis that the Vikings reached North America receives today much additional supporting evidence. Recent DNA analysis by citation 47 reveals 4 families in Iceland that possess genes typically found in Native Americans. As the island was isolated from the 10th century, the more likely hypothesis proposed by the authors is that the genes correspond to the um, Armenian, what is it? Armenian women?
Amerindian. They're
Amerindian?
thinking American Indian, but they put it together, Amerindian.
Oh, okay. Got you. The Amerindian women who was brought from America by the Vikings around the year 1000. Furthermore, in addition to the discovery of the archaeological site of the Meadows in Newfoundland, the Viking coins have been discovered as far down south as coastal Maine. The so-called Goddard Norse coin in Maine penny. It is worthwhile noting that the historical voyage of Leif Erikson, who became the first European to visit North America over 1,000 years ago, is commemorated by the annual proclamation of October 9th as Leif Erikson Day by the President of the United States. No way we give homie his own day for discovering America before everyone else did, or whatever. That's cool. I didn't know that. In conclusion, thanks to the simple observation of skylight, the Vikings could have used polarization, a rather complex phenomenon without any knowledge of this concept. Their sunstones could have permitted them to guess the azimuth of the sun that was hidden by the clouds or below the horizon. Complementary to the sundials, they could have used these when the sun was visible, and it is worth noting that animals also use polarization of skylight due to Rayleigh's scattering for the navigational, namely at sunrise and sunset. Curiously, nearly 1 millennia after the Vikings traveled to America, the Vikings method using the double refraction calcite, which leads to Malice's discovery of this fundamental property of light and coined to the word polarization, leading to the transverse nature of light waves. The Viking method, which consists of observing the sky at zenith through a calcite crystal equipped with opening at an opaque screen, is a really powerful differential method. Indeed, it is a twofold application of Mau's law at the so-called isotropy point of the crystal, where simultaneous intensity variations are maxima, which leads to a precise determination of the axis of the polarization and then the azimuth of the hidden sun. These differential methods are also used in animals to make their compound eyes equipped with orthogonal microvilli. Today, one of the methods to detect the atmosphere of exoplanets in a condition for possible extraterrestrial life consists of the detection of polarized Rayleigh scattering by the exoplanet atmosphere. A group of telescopes at the La Palma has recently succeeded in detecting weak polarization light thanks to ordinary and extraordinary rays of calcite. Polarimetry, with its differential techniques, seems very promising in the search of biosignatures, given by citation 50, especially when they're associated to the future large telescopes like the E-ELT, which is under construction. All right. So, plausible for the Vikings to use sunstones to navigate? What are your thoughts, lads?
I think they could do it.
Vikings.
Sounds like they could do it better than them guys in the video.
You're
It's
not
still
counting the dress up factor, Ken. You're not even considering the costumes they wore. That's not
yeah.
fair.
Yeah, see, I don't see an appendix that like mentions
What? The
what garb
Vikings
they were
couldn't
wearing.
dress. The Vikings couldn't dress as good as them.
You didn't see the beard?
Yeah, the beard was kind of cool.
Actually, I just wanted to point out the significance in case people didn't catch it about the 102 degrees and the 78 degrees and what that means.
Yes, what does it mean?
We're actually talking about the 90-degree orthogonality about the polarization, right? Well, the 102 is 12 degrees positive side, 78 is 12 degrees negative side of that. In the same way that they were talking about the focal point intensity reaching its height at 45 degrees from each side, those are just a 12-degree separation instead of a 45. That's what those numbers are all about.
Cool. Thanks for that. Yeah, I get it.
Little thank you, Stone G.
So this was more, it seems like more of a supplementary kind of navigating device. Like, I know the North Atlantic is like, could get really foggy and cloudy. So this is just something that they would use when they couldn't see anything to make sure that they didn't like get completely lost at sea.
That's what it sounds like.
Well, yeah, I think it's one of the main problems with the North Atlantic being so cold. You know, that in the mornings and the evenings when the sun's going down, there isn't a lot of sun burn off, so to speak, heating the atmosphere directly over the water where you are. You can't see squat towards the horizon, but straight up, you might be able to see some blue sky. So you're essentially licking your finger and sticking it way up in the air and seeing which way the light wind is going.
Hoping to catch a little light drift.
Yeah.
That's awesome. Cool. So yeah, they probably had another method, and then this was their backup.
Exactly. The last resort is get the crystal, Ned.
Get the pocket crystal, boys. Awesome. All right. Well, thanks everyone for tuning in. If there are no further questions, comments, or concerns, we'll go ahead and wrap up this Aether Cosmology episode. All right, there appear to be none more of those, so I'm going to go exit out. Be back. All right, let's check out the YouTube chat here. What do we got going on? We got the lads down here. We got Shalom, Shane, TM, PJ, Bredimus, Bogan, Melissa, Cosmo Hacking. Shout out to the boys, Mr. Xavier, Mad Mac, Jason, A-Rim, not to be confused with Aaron. All right. We'll see you guys. What are we doing Friday? Well, we're going to do Twitter community night on Fridays. We'll tap in with the lads and ladettes over there on the Twitters, see what they're up to. And Sunday will be Glowbusters, where I'll be getting into the history of latitude and longitude from the perspective of the Chinese. So the history of their celestial navigation and cosmography. And we're also going to be going over that on Sunday with the Czech lads too. So if you want a triple feature of that, you can watch last week's Aether Cause episode. You can watch this Saturday's Czech stream, and you could watch this Sunday's Glowbusters. And if you watch all three of those, you will successfully absorb all the information about the graticule, and you will make it submit to you, and it will beckon to your every call. All right. See you guys throughout the week.